7. We're going to be doing 3 reactions in this experiment, okay? So we're ramping things up quite quickly here. The first thing we're going to start with is ethylbenzene, all right? So that's what you're starting with this week. And we're going to react that with NBS and benzoyl peroxide. So I'm going to fill you in on these guys here in just a second. And we're doing this in hexane. And we do it at reflux. We're adding heat to it. This is our step 1 reaction. And we'll be making bromoethylbenzene. And so that will be our step 1 product. So, first of all, our NBS, okay, is N-bromosuccinimide. Right? And so this is our N-bromosuccinimide. Right? And we are using this as a source of bromine for this reaction, okay? And the reason we're doing that is because as the reaction progresses, it slowly gives up its bromine, versus if we just put Br2 in that reaction, we'd have a really hot, really fast, maybe out of control reaction, okay? So this is our source of bromine, is the N-bromosuccinimide. Once it reacts, gives off its bromine, then it forms a byproduct succinimide that we'll talk about here in a little bit, okay? The next piece here, our benzoyl peroxide. This guy. We'll talk about this guy here in a little bit. This is our initial source of radicals for this reaction, okay? And it's because of this bond here is not super stable. It's really easy to break that bond there, all right? So from our bromoethylbenzene, next week then we are going to be reacting it in quinoline. So we'll talk about this next week, why we're doing it this way. This is our quinoline. This is our step 2 reaction, and what we're going to do is we're going to remove our bromine and a proton, and so this reaction is a dehydro because we lose the proton, and halogenation because we lose our bromine, okay? And so what we form is we're going to form styrene, all right? And then we're going to take that on, and draw this down here. Use what's called AIBN. I'll show you that here in a second. For step 3, and this is a radical polymerization. And so then what we are going to form from this is our polystyrene. So this is CH, but this bond to the carbon goes on to the other chains here. And we'll talk about this more next week. But here is our polystyrene. And this piece that comes off the end here is from our AIBN. And so the AIBN is this guy. Which is also very reactive and another source of radicals. So the AIBN stands for 2,2' azo-bis isobutyronyl nitrile. Can't even get it out today. I'll have it in a little bit. I'll give you a list of reagents. I'll also have it on there. But this is our AIBN that we're going to use in our third step, and it's this bond here that really likes to react. Okay. So this is the overview. In a little bit here, I'm going to go back to our step 1, and we'll talk about that one in a little more detail. All right. So before that, we kind of need to talk a little bit about polymers and why those are important. And then we'll get back to talking about the experiment. So kind of a review here a little bit, hopefully. Polymers start with our initial linking units are monomers, and we put those guys together as a dimer, and then we can make a trimer. And then eventually we can put a lot of them together and we'll make our polymer, okay? So we'll start with a small molecule and end up making a really large molecule with the polymer. And so polymerization is that chemical linking of those polymers together. Now, there's always been naturally occurring polymers, all around. We've got DNA, RNA, all sorts of naturally occurring large monomer chains throughout. But the humans making them and the big polymer industry started at the start of World War II. And so what happened is there wasn't really a big drive for synthetic polymers yet. But then all of a sudden with World War II, there was this huge need for rubber for all of the different pieces of equipment that were going to be needed to fight the war. And a lot of the rubber at that time was coming from naturally occurring sources. So what needed to happen is, instead of just getting it from naturally occurring sources, we needed a way to synthetically have the rubber available. And so this is the sequence of what happened as far as polymer use. We had our naturally occurring ones, and then we modified those naturally occurring ones, and then eventually we were synthesizing the natural polymers, and then eventually we were making polymers that weren't naturally occurring, things that had never been seen before. And so it was the U.S. getting involved in World War II that spurred this on. And it was identified as the biggest threat to the country at the time was being able to come up with enough rubber. So originally, the natural rubber that was being used worked pretty well. You could get it to hold its shape fairly good after you would stretch it, but it kind of would get stretched out after a lot of use. So we needed something that was going to be more durable and more reproducible after many uses, what was going to happen. And so eventually vulcanized rubber was introduced. And so what happened, it was taking the strands of rubber and putting cross links in between all the strands of rubber. Then when it was stretched out, it would shrink back to what originally was. And so then that was much more useful and could be used many more times without it falling apart. So that was kind of the start of things, and now from here, I mean, we've got all sorts of polymers around us, the seats, the chairs, fabric, the flooring, the boards, all sorts of things are made of different polymers. there's many different architectures that can be taken on by the polymers. You could have things just linked together, one right after the other. That's what you're going to do with your styrene, is just going to link things all in a line. You can make a line of different monomers and then start branching things off of them. You can start from a common center and then have this star architecture where it just is branched off this common center. Or like the vulcanized rubber, you start with strands of the polymer strands, and then you start adding things that link those strands together, so you get this cross-linked network. And then, getting into really big things, this dendritic type of architecture where you have this common core, but then from the core it branches off, and then those branches branch off, and then it keeps branching from there. Okay, so these are just different types of architectures of polymers that can be taken on depending on how things are being put together or how they occur naturally. Now, another thing you can do is, instead of just having the same monomer over and over again, you can link multiple different monomers together. So you can have copolymers where you have more than one monomer in the polymer that you're putting together. So you could link, have some sort of pattern where you link a couple of one monomer, then a couple of another, back and forth, or make it some sort of random linkage where you just kind of mix things together, see how it falls out. You could put different, one set of monomers together and another set of monomers together, and then link them in the middle, so you've got blocks of different monomers. Or you could devise something where you've got different the different types of monomers just alternating back and forth. So it's different ways that you can put the copolymers or more than one type of monomer together. So some examples are, for example, plastic wrap or food wrap or saran wrap. You take ethylene and acrylic acid and you're putting those copolymers together, okay? And so the ethylene gives it this strong, rigid backbone, and then the acrylic acid, because it's got that acid piece off of it, makes it sticky, okay? And so this is what sticks to the glass and makes the plastic wrap actually stick together, is these OHs hanging off that then can hydrogen bond with glass, okay? That's why plastic wrap will stick well to things that are glass, but it won't stick as well to things that are plastic, because it doesn't have anything there to link these OHs onto, okay? So for food wrapping, you've got this copolymer of ethylene, so it's mainly ethylene with a little bit of acrylic acid, about 15 to 20%, so that it's got that stickiness to stick on the outside. Another type of copolymer where you just link the alternating monomers together is a dipoyl chloride and 1,6-hexane diamine. That is what is used to make nylon. So I don't know if you've seen that demo before, where you put the two layers together and then you pull with a wire at the center, and that's the nylon being made at the center of the dipoyl chloride and the hexane diamine. But that nylon is then the alternating polymer, and you just go, it's just alternating back and forth. And so that's how that one is made, and it's very similar fashion, like this is the demo, but very similar fashion. Nylon fabrics and nylon pantyhose, things like that, are made in this similar fashion. So it's like the combination of the two things make it have its rigidity as well as its stretchiness. So here, back to our styrene, which we're going to make next week in our step 2. We've got the monomer that has a molecular weight of 104.5. But polystyrene itself can have a huge range of different molecular weights, somewhere between 500 grams per mole up to 400,000 grams per mole. And usually it's somewhere in the 50,000 to 150,000 grams per mole. Now the polystyrene you guys will make, we're not going to do anything to make it a certain chain length or a certain molecular weight, it usually ends up in the upper thousands to the tens of thousands molecular weight as far as the size of your polystyrene. So we'll talk about it next week, but eventually you'll be submitting your polystyrene for sampling to see what is the molecular weight of your polystyrene. How big is it, the polystyrene that you made? And so the properties of the polymers, not just polystyrene, but in general, depend on what is the molecular weight, how many monomers do you have being put together, what is the chemical composition, so like with the food wrapping where you've got the OH groups coming off to make it sticky to the glass, what is the shape or the architecture, and then also how is it processed? What do you do after you make the compound? What do you do kind of as the finishing for the finishing product of the polymer? And so like I said, with your polystyrene, we're just going to make it. We're not going to do anything that really controls how big it is, or you know, what does its shape look like? It should just be linear. But there still will be a lot of variation amongst people's different samples of polystyrene. And so I'll talk about that more next week, and some things to be careful of in the synthesis so that you end up with some decent polystyrene. So that was kind of just the general overview and history of polymers. Now I'm going to get back to what we're doing this week, talking about specifically our step 1 reaction, okay? So again, we've got our ethylbenzene, and we're reacting it with our NBS in the presence of the NBS, and then we'll also have our benzoyl peroxide, and we're using hexane as our solvent. And again, we're doing this at reflux. We'll end up with our bromoethylbenzene. Okay, and this first first step in the sequence, I've already talked about how the benzoyl peroxide is a radical initiator. So this reaction is a free radical substitution, okay? So we're going to look at what is involved with all of that. Okay, and so couple things to be careful of when we start heating this reaction at reflux. It may just kind of start doing a nice calm reflux, but you've got to keep an eye on it, and you may potentially be turning the heat down, because as soon as that benzoyl peroxide starts reacting, so as soon as we give it some heat, we're going to go to this. Then we've got some radicals in there, and that's going to jumpstart everything going. So then it may get a little bit warm. You'll start seeing it all of a sudden refluxing more. So you have to keep an eye on it, and you may be turning the heat down because it gets going so rapidly. But then after that, you'll still have to keep an eye on it, because then it will kind of calm back down again, and so you want to make sure that you don't have it completely stop refluxing on you, and you have enough heat on it, okay? So unlike a couple weeks ago, where once you got your reaction going when you were making the sodium myristate and things reflux nicely for an hour, and once you got it going nicely, it just stayed like that, this is going to be one that you really have to pay attention to what's going on, because of the different stages of what's happening as far as the radical chain reaction, okay? Now that N-bromosuccinimide, it is going to give off a byproduct IVN since we're not using it this week here. It's going to form succinimide itself, and then this is what gives us our Br2. So the N-bromosuccinimide reacts with HBr, which I'll show you here in a little bit where that comes from. And then we get just succinimide. And then this is our source of our bromine. Now the problem with the succinimide is it's this great looking off-white solid. So it looks like it should be your product. It looks like when you're done with your reflux that you have this great solid in there and that you should be filtering away and collecting that solid, and that's what you want. But that's not the case. We're going to filter off the solid, but we're going to filter it with gravity filtration. So remember, when we don't want the solid, we always use gravity filtration. We're going to filter off the solid with gravity filtration, and what you want, your product, your bromoethylbenzene, is a liquid, and it's dissolved in the hexane, okay? So the succinimide is going to end up going, once you filter it, it's going to go into the organic waste with acetone, okay? So you'll end up with your filter paper after gravity filtration, let it kind of dry out a little bit, and then you're going to scrape all that solid into the organic waste and rinse it in with, it'll dissolve with acetone, rinse it in with acetone. And then that filter paper is going to go in the filter paper waste that's in the reagent hood. We don't want to throw that in the garbage can because it really, the ethylbenzene smells, our bromoethylbenzene smells, it's got a really high stench on it, and it's still going to have chemical residue on it that we don't want to throw away, okay? So that filter paper will go in the filter paper waste. But just don't be tricked by the succinimide looking like that. Is that nice? You're thinking, oh yeah, there's my product right there. It's not. It's the byproduct. It's what we don't want, okay? So then after you form your bromoethylbenzene, and we filter off our succinimide, we're going to go through and distill off the hexane just as you have previously with simple distillation. We'll use a water bath, distill off our hexane, and then you're going to bottle up your bromoethylbenzene, okay? Now we have to be careful because this bromoethylbenzene is really good at reacting with itself, okay? And doing reactions on its own before we get to actually using it to make the styrene, all right? So once you get your product, you're going to want to make sure that you keep it in a very dry, tightly capped vial that doesn't really have, make it a small vial, not a really large vial. You don't want any oxygen in there. And you want to keep it in the dark because with that halogen on there, it's very reactive and it's also very light sensitive, and it may just react on itself just sitting in the light. So once you get your product after the distillation, get it in a vial, cap it, know the weight of that vial and cap before you put it in there, then it's easy to get the mass. You'll also want to get the volume. We'll need that next week for some yield calculating. And then just make sure that it's in that tightly capped vial. Even while, we'll talk about here in a little bit, there's some tests you're going to do. You still want it in that vial while you're doing that. And then eventually, you're going to keep it in the dark. So put it at the back of your hood in a beaker where it's going to be safe, and keep it in the dark as much as possible. Write down what it looks like. Make sure you make observations of what that product looks like, because what you end up having next week in that vial may look different than what you've got this week, because it may change just on its own in a week, okay? Which is fine, but make sure you note what it looked like this week versus what happens next week. It may start turning colors on you. There may be things that form in the vial. All sorts of things can happen because this is so reactive. So at this position, the benzylic position, why is this so reactive? And it's not just this this compound, but benzoic positions in general, why are they so reactive?
Have a pretty stable radical when light.
Well, we're going to talk about here in a second, you are going to form a radical there. And because of this aromatic ring, you end up with multiple resonance structures that help stabilize that radical on that carbon, okay? And so that's what makes this carbon so reactive. But it's not necessarily always radicals. If you end up with a carbocation in the benzoic position, that's also going to be really reactive, okay? And so this aromatic ring is what's helping to stabilize that, and that's why we get things reacting with our ethylbenzene versus anything reacting with the hexane, because there's not really much difference between hexane and ethylbenzene. It's just a bunch of carbon and hydrogens, except for that aromatic ring. That resonance stabilization is what makes it so reactive at that position, okay? So let's look at the radical chain reaction that's involved. So it talks about that benzoyl peroxide being kind of our initial source of radicals. So it kind of just throws some radicals out there, okay? So we're not going to talk about it in terms of our different steps of the radical chain reaction, but know that it's just out there to get the radicals started, and then from there we kind of follow in these steps, okay? And so our radical substitution reaction, what do we, when you're talking about radical chain reactions, what do you always start with? Initiation, right? So our initiation step is our bromine that's generated from our succinimide, okay? So we'll get to how that happens here in a second. Then reacts with any heat or light, which we will have both, because we're not going to turn off the lights while this is happening, okay? And we get bromine radicals out of it, okay? So that's our initiation step. Then our propagation steps, we've got two of them, okay? Our first one, we're going to take our ethylbenzene, and we're going to react it with one of those bromine radicals. Okay? And so remember, when you're showing the radicals, they're just single side, you know, it's not the double arrowhead, it's just one side of the arrow here. So one of our radicals is going to go on this carbon, and then we're going to react with this bromine radical here, okay? And so when we do that, then we get our ethylbenzene radical plus our HBr, which is then used to get the bromine off the succinimide, or the N-bromosuccinimide. Our second step is then, okay, we've got our ethylbenzene radical. And then it is going to react with another Br2. And we've got it reacting with one of the radicals, and then the other one goes on with the other bromine and forms more bromine radicals. So now we've got our bromoethylbenzene, and then we've got more bromine radical to go into this step again to keep brominating the bromoethylbenzene. Then our termination step is any two radicals combining. Then once we've got our radicals combined, this isn't going to be reactive anymore. And so once we get our benzoyl peroxide going, we get this whole situation going, and then eventually it starts dying down because we get our product forming and we don't have more MBS to be thrown into it, and we don't have more ethylbenzene to be reacting, okay? And so during this, you will also potentially see different color changes in your reaction. So the bromine is like, if you remember experiment 6, the bromine solution was kind of orangish reddish color. You might start seeing kind of orange colors forming in your reaction as that bromine's being generated and then being consumed, okay? Yeah?
Are we going to need this initiation propagation, the radical reaction in our notebooks?
I would show it for reference, yeah. I mean, as far as the reactions, those are the reactions, but it's also a good idea to have this information in there, as well as part 3, we're going to have another radical, with radical polymerization.
So like for the pre-lab though, in our reaction section, do we need to show like just those ones up there, or do we need to show like all of it?
Well, that was I think what the question was, and to start with, yes, those are your reactions, but it's always, because so much is going on and so much is involved with the different reactants in this case, it would be a good idea to also show this as well, the steps of your radical chain reaction. Okay. All right. I talked about once we're done here, once we're done refluxing, then you're going to filter off your 6-amide, you're going to distill off your hexane, and then you're going to put your bromylethylbenzene in a vial after you've got the mass and the volume. And then we've got some tests we want to do to make sure that we have actually done some sort of chemical transformation. This is how we will kind of confirm that we went from ethylbenzene to benzene, all right? So the first one is density relative to water. And you're checking this with both ethylbenzene and then you're checking this with your bromylethylbenzene. Okay. So you're going to have 2 test tubes, all right? And you're going to put about 1 milliliter of water in each one, all right? In the first one, you're going to put just a couple drops of ethylbenzene. So out of the reagent container that you got your initial ethylbenzene for your reaction, you're then going to get a couple drops of ethylbenzene and see what happens relative to water. Is it floating or is it sinking? So if it floats, what does that tell you about its density? If it's floating on top of the water, less dense, right? If it's sinking, more dense, okay? So ethylbenzene, what do you think is going to happen? It's just carbon and hydrogen. Less dense, right? Like if you think about like experiment 1 that was hexane, it was the top layer versus the water was the bottom layer, okay? So typically when it's just carbon and hydrogen, it's going to be less dense than water. Our product from this reaction now has a halogen on it. What do you think is going to happen to density relative to water with your product, with your bromylethylbenzene? It should be more dense. Usually when you have halogens relative to water, they're more dense than water. So like if you look at halogenated solvents, like dichloromethane versus water, water will be on top, dichloromethane will be on the bottom, okay? So that should happen with your product. Now, if you don't get all the hexane off, what is going to happen? So when you do the distillation, you don't get all the hexane off. Well, you'll still get 2 layers regardless, but what do you think will happen with your product? Will it float or will it sink? It may end up floating if you don't get enough hexane off, because it'll end up being less dense with all that hexane around it, okay? So for your distillation, you want to try and push off as much hexane as possible. Otherwise, this test may not work out so well, okay? You may end up getting conflicting results. Or sometimes you get kind of 3 layers. You'll have some that floats and then water and then some that sinks because you have the hexane and the bromolethylbenzene in there, okay? So if you get conflicting results, it's most likely you still have some hexane on your product. The other thing you can consider, you're starting with 5 mils of ethyl benzene. So about how much product volume-wise should you make? 5-ish mils, right? So you want to store it in one of the small vials, which is 7 mil vials. If you have so much product that it doesn't fit in a 7 mil vial, what does that tell you about the hexane? You probably still have some hexane left on there if you've got more volume than the 7 mil vial, okay? Now the second test, so this was our first test, okay? Our second test is we're going to use silver nitrate. So do you remember silver nitrate from Gen Chem? What did it do in Gen Chem? Do you remember any observations from Qual and Gen Chem when it reacted with halogens? Anything? So in this case, we're taking our product, which is halogenated. We're going to react it with silver nitrate. And this is all like the silver nitrate's in ethanol, and we're also going to use ethanol to get this soluble, so we don't have to worry about it like crashing out of something that's aqueous, okay? And so what happens is we end up forming this guy, plus then our silver nitrate becomes silver bromide. So we get this solid that's formed, okay? And that solid is like off-white or kind of yellow-white solid, okay? It's kind of off-white to yellow solid, and once that confirms that there's a halogen present, because if there's not a halogen present, you're not going to get this reaction, okay? Now this reaction, it does sometimes take a little bit, like give it a good, 5-ish minutes to be judging whether or not you see a solid or not, because sometimes it does take a little bit. Also, when you get the silver nitrate and your ethyl benzene all in the ethanol, kind of tap the side of your test tube a little bit so that it actually mixes. And then hopefully you'll get a positive silver nitrate test, okay? Now if you end up with kind of conflicting density tests and you get a good silver nitrate test, you probably want a second confirmatory test. So what's another test that you could do based on things we've done in the past to test for a halogen? You could do the Biopsying flame test and make sure you get a green flame. So if you end up doing that, don't stick the copper wire in all of your product from this week. Just take just a tiny little bit out and put it in a test tube and then do the flame test. But that would be another test that you could do, is the flame test, and hopefully you get a green flame, because hopefully there is a halogen present, okay? So then next week, regardless of what your product looks like, which it may, like probably at least half of you, it may kind of turn a little color, so that's fine. We'll keep going with it, and then we'll see how much styrene we get out of there, and then go on to make our polystyrene. So to kind of help you guys out with information for this week, I've kind of put like half or part of a table of reagents together. So it's kind of partially there. We've got molecular weights, boiling points, melting points, depending on what applies, densities. Down here are some things that still need information. So the styrene, the methanol, and the THF, this hasn't been filled out. So you still need to fill out information here, okay? And then over here, in the amount in moles, none of that has been filled out, okay? So based on what your instructions and your lab manual says, you're going to figure out how much to use, and then based on that, you'll also figure out how much you're going to produce, okay? So I'll leave that there for a second. Also, in your pre-lab, when you're writing, you have 3 reactions to take care of, okay? You also need to figure out yields for the 3 reactions, all right? So steps 1 and 2, you're going to calculate regular theoretical yields. And then show the sample calculation for how you would calculate percent yield, all right? And so for theoretical yield, you're going to have to go off of what are you supposed to be starting with, okay? So starting with the 5 mils of ethyl benzene, going from there for steps 1 and 2, okay, if I got 100% yield out of step 1, that would be my starting material for step 2. Use that to then figure out your information for step 2, okay? So assume you get 100% conversion, all right? For step 3, where we make our polystyrene, we can't really calculate a theoretical yield. So what you're going to calculate is you're going to take your grams of polystyrene divided by how much styrene you put into it. That times 100%. So what type of calculation does that look like? Percent recovery. And so that's what you're actually calculating for step 3, is you need a percent recovery, okay? So for your pre-lab, you're going to have a purpose that takes care of the 3 steps. You've got your reactions you're going to show. You've got a physical data table that kind of got a good start of. You'll show any new equipment you've got, and then references, and then when you get to the yields, steps 1 and 2 are going to have theoretical yields that you show and how you would figure out percent yield. Step 3 is going to be a percent recovery calculation. Okay. Questions? All right, I'll leave this up here. Just make sure if you come up to look at it, don't block anyone from being able to see it.
Actually,